All right, so this section of notes is dealing with the second half of chapter 2, which deals with water. And so, why do we spend time dealing with, talking about water? Well, we know water is kind of the fundamental, foundational component to living things. You have to have water in order to have life. That's why they talk about, finding water on planets is an interesting sign of, the possibility of life. One characteristic that makes water so important for us on this planet is its ability to form hydrogen bonds, because water is a polar molecule. And if you remember from chemistry, polar means that one end of the molecule has a positive charge and one end has a negative charge. And so in a water molecule, H2O, right? You have two hydrogens. Those hydrogens the one electron that each hydrogen has is being pulled towards the oxygen more heavily, more strongly. And so that oxygen end is negative and the hydrogen end is positive. And so that creates a polarity in the molecule, which allows water to form hydrogen bonds. Why does that happen? Well, oxygen, we know, is a highly electronegative atom. Again, remembering back to chemistry, what does that mean? It means it has a strong need for electrons to fill its outermost shell. It needs 2 electrons, right? Its atomic number is 8, which means it has 2 electrons in the first shell, 6 in the second. It needs 2 more to be stable, and so it will pull those electrons towards itself. And that ends up creating a partial, as you can see down here, a partial negative charge on the oxygen and a partial positive charge on the hydrogen. And these are all just different versions of models of water. The Bohr model, which is maybe what you looked at in chemistry a lot. Then, of course, the ball and stick, looking at angle, degree, and then just the space filling model. The space filling model, it tends to be the one that we use most commonly in biology. So some of the things that hydrogen bonds do for living things, actually the main thing, is that it allows water to stick to water. It allows what we call cohesion to occur. Cohesion is like sticking to like, so it's water sticking to water. And so when those water molecules are attracted to each other, the bonds of attraction are called hydrogen bonds. So the partial positive hydrogen on one water is attracted to the negative charge of the oxygen on the other water. It's not a bond in typical terms where electrons are being exchanged or shared. It is just a bond of attraction. So these bonds, because they're bonds of attraction, like magnets, they're weak individually, but together, collectively, they make quite a force for that body of water. And so because of water's ability to be cohesive and create hydrogen bonds, we have a lot of physical properties that are created because of this ability. So we already know what cohesion is. Cohesion is when water sticks to water. So if you look over here at this beaker and the capillary tubes that are in the beaker, you can see the water climbing up those tubes. And that happens when you stick those hollow tubes in, and you get different heights in the water column because of the various diameters. But what that's showing us is both cohesion and adhesion. And so, this water strider is able to walk on water because of the cohesive surface tension created on the surface of the water, that film, if you will, of water, because those water molecules are sticking to each other, and they have a little support right under them from the water molecules under them, and it creates a very, very thin film, but light things like water striders can float on the top. But over here to the beaker, the water is moving up that capillary tube, but we call that capillary action, when water moves up very narrow channels, because the water is sticking together, so it's being pulled up that capillary tube, not because of cohesion, but because of adhesion. The water is sticking together, and I guess in a way than being pulled up because of cohesion. But because water is stuck and attracted to things with charges and other polar molecules, glass is a substance that has charge. It has components in it that are polar and have charges in them. So that water sticks and is attracted to the charges in the glass, and so it pulls that water up the capillary tube by sticking together, being held together by cohesion, but then also sticking to the sides of the glass and literally climbing up the sides of the glass. So, other properties of water here. We know water has a high specific heat, which means it takes a lot of energy to change water, like 1 degree. So, and we see that, or we feel that, in the spring when you open a pool or you jump into a pool for the first time, it's going to be really cold. Why? Because it takes a lot of heat, to change the temperature of the water, because you got to break all those hydrogen bonds, because it takes energy to go into those bonds, to break those bonds, and then increasing the movement of the water molecules, which then we have increased temperature. Water has a high heat of vaporization, which means that when we sweat, sweating is a characteristic that some animals have, like us. And so when you get hot, you start to sweat. Well, the sweat doesn't cool you off, but the evaporation of the sweat off the surface of your skin is what cools you down. And because water has a high heat of vaporization, it can pull a lot of heat out of your body through your skin and take that heat, put it into the water of the sweat, and then evaporate the sweat, cooling the surface, then leaving the surface cooler than what it was, because it used that heat to evaporate the water. We also know that solid water is less dense than liquid. Why? Because when water, it's one of the few types of substances out there that, everything as it cools slows down. The molecules slow down, they get closer together, they get more dense, and they sink. Well, water, when it hits 4 degrees Celsius, unlike other things, when it hits 4 degrees Celsius, it actually spreads out and it forms kind of a crystalline lattice type structure. And so you have air that gets trapped between those water molecules, within those, between those bonds between the water molecules, and that air that's trapped makes water be less dense as a solid than as a liquid. So that's why ice floats. That's why, lakes freeze from the top down in the wintertime. If they froze from the bottom up, we'd have, no aquatic life left in bodies of water in very cold environments. Right. So this is another characteristic or property of water, is that it's a very good solvent. Why? Because again, it's polar and it has partial charges. And so those partial charges of water, like the negative end of the oxygen, is attracted to the positive charge on ions. So if this is our salt crystal, right, made up of sodium and chlorine, our chloride ions, and we know sodium has a positive charge and the chloride ion has a negative charge. How do we separate that? How does salt actually dissolve in water? Well, when you put that salt crystal into water, the water molecules attack it, if you will, and surround each ion with a hydration shell. That's what we call that, a hydration shell. And so water molecules basically isolate each ion and separate them, and that's how they end up dissolving material. That's also how you get saturation, which means that all the water molecules are engaged and busy in these hydration shells, and there's no more water left to dissolve any more solute. And so that's how you end up getting like a bunch of sugar in the bottom of a cup of iced tea, that you can't get to stir in a cup of iced tea, because the water is all the free water molecules have been used to dissolve the sugar. So that's what number 4 was about. Number 5, It says it organizes nonpolar molecules, which is kind of an interesting way to put that. But hydrophilic molecules like water, that means they're polar. They have charges, like um, things are attracted to like in this case, meaning polar to polar. So if you have something with a positive charge, it's going to be attracted to the negative end of something else. We call those molecules hydrophilic, water-loving. Hydrophobic things, water-fearing, are non-polar substances, things without a charge. And so what happens then is water causes those hydrophobic molecules to kind of, coalesce and aggregate and form together into various shapes, coacervates, and other things that form when nonpolar items are kind of wrangled by water. Water can form ions. It can break down into hydroxide and a hydrogen ion, right? An OH and an H. And we know that water is tied to the idea of acids and bases, because pure water has a pH of 7. It is a neutral substance, not acidic, not basic. And pH of that substance, remember, tells us how much hydrogen, what the concentration of the hydrogen ion is in a specific solution. So when you have water and it's dissociating into hydrogen and hydroxide, it has a pH of 7, meaning that the hydrogen and the hydroxide ions are relatively even, right, in that solution. But an acid, so if you're not talking about water, but you're talking about another substance, for it to be considered acidic, it is a substance that when it breaks down in water, it gives off hydrogen ions. This arrow here, by the way, means that that the plus sign is supposed to be a superscript. It doesn't translate very well, but a down arrow would mean a subscript. So an acid is anything that when it breaks down in water gives off hydrogen, and therefore the pH becomes lower, because the higher the hydrogen ion concentration, the stronger the hydrogen ion concentration, the lower the pH. Okay? A base then, on the other hand, is one of two things. It is either a substance that takes hydrogen out of a solution, right, combines with hydrogen that is dissolved in the water. And if you're taking hydrogen out, then you're lowering the hydrogen ion concentration and the pH increases. A base is also something that can give off hydroxide ions as well. And so here's the pH of some, basic things that maybe we don't think about as being, a strong acid or a strong base. Bleach and ammonia. The Salt Lake has a pH of 10. Of course, your strongest acids are hydrochloric acid, stomach acid, etc. Most body fluids tend to be in the close to neutral. Urine does tend to have a little bit more of an acidic lean to it, but most body fluids tend to be neutral. So a buffer then goes hand in hand with acids and bases, especially in living systems, because we have to keep our pH balanced. That's not just a commercial for a secret deodorant, but we do have to keep a neutral pH in most places in our body, besides our digestive tract. So a buffer is, in chemistry you might have dealt with them too, but in living systems we have natural buffering systems that help resist changes in pH. If a solution becomes too basic, then the buffer will give off hydrogen ions. If that solution becomes too acidic, then it will take hydrogen out or absorb hydrogen from that solution. So it's kind of like a teeter-totter. That's kind of the way I think of it anyway. A buffer is a teeter-totter that helps keep that teeter-totter right in the middle, and prevents major swings in pH. And so again, we have a lot of biological buffers. One very common one is the bicarbonate or carbonic acid buffering system, because carbon dioxide is being carried through our bloodstream, from our muscles back to our lungs. and out of our body. So when carbon dioxide, however, combines with water, it forms carbonic acid, which we don't like. So we have bicarbonate ions, which can help with the buffering system to reduce that influence of the acid in our bloodstream so that our pH can stay neutral.